I'm Sunny Shell, and tonight joining me is Dr. Tapiocaweasel, or Vandy, a frequent contributor on Bad Science Sunday. So sit back, buckle up, and let's get to the sunny spot on Skeptic Haven. Good evening, everyone. Welcome to the sunny spot. Hi, Vandy. How are you doing this evening?
I'm doing great. I'm happy to be here.
Excellent. I'm happy that you are here. We've been trying to get you on now for a couple weeks, and so I'm glad we were able to finally get it worked out. So for our viewers, I would love it if you could just tell them who you are. Who is Vandy?
Yeah, I go by Dr. Tapiocaweasel on YouTube and just Tapiocaweasel, sans the doctor part. Most other places, but my name is Michael Vandergraff. I am a postdoc in physics at Stanford University, and I study. I'm an atomic physicist, and I do ultra cold atoms and stuff. And we're building an experiment to study gravitational waves with them. And then on YouTube, I co-host a show called Bad Science Sunday with Maya Adkisson, and we react to we react to bad science. Except she doesn't let us do flat Earth because apparently that's too much for her. So
I don't blame her. It can get to anybody. So, and that show is awesome, by the way. If you have not checked it out, y'all have got to do that. And I believe we have a link in the description, so y'all need to go and check that thing out. So before we get started I have a whole lot of questions for you. But the first thing is, I want to talk a little bit about your grandfather, because you come from an interesting lineage. So who was your grandfather?
Yeah, so my grandfather was his name was Robert J. Vandergraff, and he was the inventor of the Vandergraff generator. It's that metal ball that you put your hand on it and your hair stands up.
That's so
And
badass. So
yeah,
cool.
it's super. The joke I like to make to people is that my grandfather was basically Thor, because when you get those, when you make big ones, the sparks that come out of them are no longer sparks. They're like lightning bolts, and they'll fry you if you're in the wrong place. That's why you gotta be in a Faraday cage and everything, and they can get real loud and powerful and nuts. So that's the joke I like to make. But he did that oh man, 95 years ago, I think now, almost. Yeah, I think he got the first one working in 28 or 29, 1928 or 29. Which, by the way, is an indication he waited quite a long time to have kids, and then his son waited quite a long time to have kids too.
Yeah, what are you, like 60?
Yeah, right? Yeah, no, I'm 32, but yeah, he was born. My grandfather was born in 1901, so
Wow.
um,
Wow.
but yeah.
So what type of influence did he have on you and your field, the choice that you had in your career?
Yeah. Well, hold on. I will be right back.
Okay. And I will Vogue or something to do something while he's gone. I'm not good at any of that stuff. If you have any questions for our wonderful guest, be sure and put them in the chat, and I will put them on for him, and he can answer your questions as well as mine. Okay, go ahead.
I'm so sorry.
That's okay.
My landlord suddenly showed up. And I was like, can I talk to you a little bit? Anyway, so unfortunately, my grandfather died in 1967, so I never had the opportunity to meet him. And I work in a field of physics. I work with ultra cold atoms, which is very, very, very low energy. You can't really get colder than the sort of systems that I work with because they are very near or in the quantum ground state, Whereas my grandfather, what he did with this, with the generator, is it creates a giant electrical potential, and then you put a charged particle next to it, and it goes booming away really, really, really fast. It's one of the first, it's one of the earliest types of particle accelerators. And actually, if there was a team that if they had turned on their accelerator and just aimed it at a target, if they had done that 1 week earlier than they did it, they would have been the first people to split the atom. But instead, they were being careful and like waiting, and somebody else used a similar type of machine called a Kroghoff-Walton one, I think. But yeah.
Well, so what made you decide to go into this field?
Oh, I've always really, really been interested in physics. And I think that that's probably one of the biggest influences that he had on me, sort of kind of vicarious. Like my dad was a physician, not a physicist, but he was very interested in physics, and it was always like an interest of mine growing up. And I was always good at it. So if you like something and you're good at it, it makes a lot of sense to go. And also, I mean, people assumed I was good at it too because of the name.
Yeah.
So the reason I went into physics was because I think it's just so cool. And the reason I went into my particular like subfield, atomic physics, and specifically like laser cooling of atoms, is because it's just so cool. It's just so cool that I'm able to, with a bunch of stuff that's like on a table and some instruments on a rack that you plug into a wall, if you get everything just right and you get the magnetic fields aligned and you get all the laser beams pointed at the right spot, that you can take a vapor of hot atoms that are they're up hundreds of degrees Celsius, and you can cool them all the way down to well below a millionth of a Kelvin above absolute zero. And I just think that's so cool. And you can see things that very clearly show how matter behaves like differently in these regimes. You can sort of watch as you can take two atom clouds and sort of make them go through each other, and you'll see a halo, a spherical halo that shows you exactly how a small percentage of those atoms sort of bounced off each other and scattered. And it boils down really nicely to a textbook problem and a demonstration of the S-wave scattering length and stuff like that. And I know that, sorry.
No, I'm
so cool.
This is what I love. I love to hear, because that's not my field, and yet I'm very, very interested. And I've been interested in science, physics, astronomy, all of those things since I was younger. But I go into political science and psychology. Don't ask me why. Although I do love it. But I love hearing all of this. We do have a couple questions from our chat. The first one I want to pull up is from Titan Uranus. See what I did? He always wants me to say. What would happen at absolute zero? That's a great question.
Yeah. So the thing about quantum mechanics is that it imposes a lower limit on how well you can know the momentum of a particle. And momentum is going to be proportional to temperature in this case, or there's a square root or something, right? And that's the Heisenberg uncertainty principle. You can only know your momentum as well as you don't know your position. So if you kind of know where your atoms are, then you can't know their momentum very, very, very precisely, which means it has to have some spread. It can't be zero, because if it's zero, then you know it, right? And you can sort of get around this by making your system bigger and bigger and bigger and bigger, because then you're very unsure where your atom is. It's like it's somewhere in this area, which means that you can be very, very sure that it's crazy, 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 crazy cold, but you're always going to have that trade-off, because the product of those two uncertainties has to be greater than some fraction of Planck's constant. So what would happen at absolute zero? What would happen is you have somehow created a system that is infinite in extent, and therefore is able to have basically zero momentum, and you can't do that. So you can't get to absolute zero. You can get to the coldest state available to a system. There's nothing colder. There's no energy state below it, but you can always make that state itself a little bit colder by changing the geometry and stuff.
Okay. Wow, my brain. That is so awesome. That is so awesome. We have another one from Phantom X11. As I understand it, the Big Bang is nothing more than where the GR model divides by zero. It isn't known for sure that it is beginning of reality. We need a unified theory for that, correct?
So the Big Bang refers to the hypothesis that the universe was initially in a much denser, smaller region of space, or that rather the region of space that we see was itself smaller and therefore denser. The hot Big Bang then, also asserts that it was very, very, very hot back then. So the Big Bang doesn't actually refer to necessarily the very, 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 very sort of beginning when the math breaks down. And the math breaking down, when math breaks down, the word for that you often hear is singularity. And dividing by zero is one way in which you can have a singularity sort of show up. But it's not as straightforward as saying that in that GR you're suddenly dividing by zero. I'm actually only just now starting to really study general relativity closely. I haven't had to, because I'm an experimental quantum person. So, but it's now becoming related to my work, because we're using precision quantum sensing to try and measure gravitational waves, so it's related. But it is correct that when you do go back, it does seem to get smaller and smaller and smaller and smaller until it's basically like at a point or something the size of the Planck length. And a new theory, a new physical theory is required to move beyond our current understanding. Our current understanding simply, it doesn't work at that level. This is not controversial. Everybody knows this. But yes, ultimately, when you're dealing with really, really, really dense systems like that, you need a theory of quantum gravity, and we do not have one currently.
Great question, Phantom X11. We are getting hit with questions. This is awesome. It'll be a long time before I get to ask you my question, but that's okay. So we have another one from, I don't know if it's Al Trucker or AL Trucker.
Al Trucker.
All right. So the question is, will we ever get to surf on a gravitational wave, use them to trebuchet ourselves across the universe by hyperfocus of gravity? I really want to know the answer to this one.
I don't know if that is in principle possible. It might be. It might be. Gravitational waves travel at the speed of light, so it wouldn't break that. But I think that if Star Trek were being written today, that would be the language that they use to describe how warp drive works. I would think. So something sort of similar to that, when you kind of stretch space and then, or compact space and then go across it all, pretty quick. So I don't know. Certainly not in our lifetime, though.
Yeah, that I was thinking that exact same thing. Star Trek immediately came to mind, and yeah. I'm gonna say yes because I believe that Star Trek is gonna come true. Just kidding. I really hope it does, though. Wouldn't that be awesome? I
mean,
love Star Trek.
we got the automatically opening doors. That was
Yeah, exactly.
you know?
And we had the back in the original Star Trek, they had the what did they call them? Where they would communicate? Would they be down on the planet and they communicate their little?
Oh yeah, they had like and yeah.
It looks like a flip phone. It's like we had that last decade, dude.
It wasn't a tricorder, was it? Because
No, I
tricorder
don't
is
think
like
it
the other
was.
generic sort of thing.
Yeah.
But yeah, you didn't. I mean, you didn't have anything as flashy as a smartphone in Star Trek. Like,
Mm-mm.
you have things that you're like, oh well, that's sort of like. But you didn't actually just have a generic thing with a big screen that like you could just do whatever on, right?
Exactly. Now, I mean, who would have ever thought we would have something like cell phones or computers or be able to talk to each other? I remember, I'm dating myself, but when I was younger, the biggest thing that I heard was that they were saying that one day you'd be able to have a phone conversation but see the other person while you're talking. It was
Yeah,
like, no way. How would we do that? That's kind
yeah,
of funny.
yeah.
Anyway,
And now I expect like 5G internet data at like arbitrary places, like just while I'm out, and I just expect to get high-speed internet on my phone.
exactly. It comes to my car, even, my
Yeah.
screen of my car. So, yeah, absolutely. We're so awesome, aren't we? So, our next one is back from Titan Uranus. Wes, you forgot the most important question. Answer yes or no. How do magnets work?
No, is my answer.
I love it. All right. And Titan is like on it. Could
He
not,
likes messing with me.
I know he likes messing with me too. Could not that density superposition not have resulted in what amounts to exactly what you said about absolute zero, infinite in extent and zero mobility, with the Big Bang, the resolution of it? That's interesting.
Yeah, so yes, but yeah, we're talking about, so the universe is a many body system. It has a lot more than one particle, and when you're talking about, which means that describing it as a wave function, sort of simplistically, that has a certain extent, which could be infinite, and then you would be potentially at absolute zero. Doesn't really work because it's actually the wave function of the entire universe, which is much more complicated than that. But you could make the argument that the heat death of the universe, as things just keep on expanding and expanding and expanding and expanding and expanding, could lead to something very much like that. And so, yes, in that sense, that would be probably the closest that you would get.
Interesting. I like that.
It,
Good question.
and ultimately, the heat death of the universe is just the Big Bang, keeps going. It's not like the Big Bang. The Big Bang, in my opinion, should be considered sort of an ongoing sort of thing, because the universe is still expanding, and the Big Bang, I suppose some people might refer to it as the start of it, but I think mostly it refers to that happened.
So. Right. Yeah. It's really just an expansion.
Yeah.
Yeah. So I have one from Wes, which is awesome. He says, what use is supercooling atoms? What are you learning that might be useful? And what would happen if you did get to absolute? Well, you kind of already answered that. So he probably put it in before then. But so what use is supercooling atoms?
Oh, it's really useful for a lot of different things. You can create extremely precise instruments, and you can measure things more precisely than in any other sort of systems that we have. Our most precise timekeeping are done with by interrogating ultra cold atoms of strontium that are in an optical lattice with a laser that is connected to an extremely, extremely stable cavity. And what all that means basically is that these atoms, they will react to a very, very particular frequency, and only that frequency. And so as long as you keep on zapping the atoms and making sure that they react, you know that your laser is at that frequency. And you can create a clock that will miss less than like a millisecond over the entire lifespan of the universe. Now, this sort of technology is necessary. Not that level of precision is not necessary for the GPS system that we all use very often, but the version of that was first figured out back in the 60s is necessary for that. If you didn't have these cold atom clocks, and they have to be cold because if they're hot, then they're all bouncing around and you don't have enough time for them to interact with your signal, and you can't be as precise. So you need them to be cold. But if we didn't have those, then your GPS simply wouldn't work. And so the more precise we get, for example, eventually we're going to have things that are just going to be able to keep time a billion times better than anything we have now. And if you have those and you just put them in a whole bunch of spots in the ground and you have a good GPS system, you would be able to detect, for example, the millimeter by millimeter movement of tectonic plates, maybe. Or you could detect directly by measuring how the atoms react, you can detect their local gravitational field. And if that changes, that could change for any number of reasons. It could change because there's seismic activity going on. And the one, as you might have been able to tell, I kind of think that I like to think of it as being able to eventually use ultra cold atoms to like predict earthquakes and stuff. By doing like gravitational measurements. And that's just so cool.
So would that also mean that you would be able to detect maybe when a volcano is about to erupt? A lot
Potentially.
Right.
Yeah, this is, now I'm going to be clear, this is not technology that application is not like in progress on any level, right. But we're building a 100-meter tall tower that is going to be doing atom interferometry at the top, middle and bottom, the top, middle, and bottom of it, and that's going to be constructed at Fermilab in the next few years, and using that to measure gravitational waves. And the biggest source of noise that you have to account for, or one of the biggest sources of noise, is just the fact that because the Earth is made of stuff and the stuff can move a little bit, it means that the amount of gravity changes just like a little bit. So if you could put this thing up in space, you would get rid of your biggest source of noise. But then you got to put it up in space, and that's got other issues. So it's really amazing when you just sort of sit down and you think about, okay, if I had a ruler that could measure this distance 1 trillion times better than anything we have now, you'd figure out ways that it's useful.
Right. Yeah. This is so cool. I just love this.
Also quantum computers, stuff like that.
Okay. So when you were talking about that, there's that, the reason I asked the question about volcanoes in particular is because, in Iceland, they had the big eruption that just took place. It's actually a fissure, a big, long, miles-long fissure that came up and is a destroyed part of a town. And, the people, though, they had those earthquakes for quite a while, and so they had to all evacuate, and they've been gone just waiting and waiting and waiting, and finally it happened, and then they get to watch, some people's houses burn and stuff. It would be so great if they could actually detect that a lot sooner and more accurately and stuff like that. That would be kind of cool.
Yeah, it's funny you mentioned Iceland. One of my favorite papers it's cool, but also because I enjoy doing things like debunking flat Earth, and I think it does it amazingly, is a paper where they used an atom interferometer and they put it on a plane, and they flew that plane over Iceland, and they measured the change in gravity due to like, oh, there's a mountain here. And when we fly over the mountain, gravity gets stronger. And when we fly east, gravity gets weaker. It doesn't actually get weaker, but you're flying with the curve of the Earth. Whereas when you fly west, you're flying against the rotation of the Earth. So you don't get the same. And it's yeah. So you mentioned Iceland, and I wanted to bring that up because it is very much yeah, you can measure this sort of stuff, and you will be able to measure it even better later.
I love that. I'm a big geek for that stuff. Okay, so if you have questions for him, please get them in. I will definitely get to them. And thank you for all those that did ask the questions. Those were great ones. So back to you. You had mentioned that you are an experimental atomic physicist. What exactly is an experimental atomic physicist?
Yeah, so in my case, it means ultimately that you're trying to either so an experimental physicist is one who's trying to sort of design, run, or analyze, or all of those things, data from an experiment, as opposed to a theorist who is doing the theoretical sort of part of the physics. They're doing a lot of the calculations and things like that, and figuring out exactly maybe what the experiment is supposed to, what it should measure under a given sort of thing. But like my day job is to actually we have a vacuum chamber, and it has strontium atoms that are getting sort of beamed into it from a little oven, and then we use lasers to basically hit the atoms and slow them down, because light has momentum, and if you do it right, then you can slow the atoms down until they're really, really, really cold. And I'm an atomic physicist because I do it with atoms. You can also do it with molecules, but it's a lot harder. And I'm studying most of the relevant physics is physics of like the electron and how it goes around the atom, and how the electron will interact with a photon when it goes by it. So that's sort of what an atomic physicist studies, is they study the system of the atom as a whole, not the nucleus, and not I'm not a particle physicist or a nuclear physicist, because the things that I'm playing with are the entire atom. So.
Okay, that makes sense. Okay, so you had also talked about quantum measurements, and we have a lot of viewers that are very well versed in these terms, but I also don't want to overlook those who don't know the thing. So I wanted to ask you a little bit about quantum measurements. Can you explain?
Yeah, so the term quantum measurement doesn't necessarily mean anything other than a measurement in a system where quantum mechanics is important. You could make the argument that a transistor just working and doing its day-to-day thing, that is sort of doing a quantum measurement. Is there current or is there not current? Because the physics of semiconductors and transistors is intrinsically quantum. You need quantum physics to describe it. But the sort of core of the idea is that we're talking about measurements where for basically, at the end of the day, the main way that I get data from my experiment is I have a bunch of atoms in a vacuum chamber that are in a little cloud, and it's a very, 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 very cold cloud. And then we shine lasers on them, and after doing all the other stuff, also with lasers, but we shine lasers on them for a few microseconds, and we get a camera and measure all of those all of the photons basically that we collect. And also in some sense, sort of, that's a quantum measurement. But the fundamental sort of idea is that the system that you're measuring, in this case, where those atoms are, is a function intrinsically of quantum physics. You can't use classical physics to describe it. So one thing that the most popular sort of experiment that demonstrates this would be like the double slit experiment.
Mm-hmm. Right.
And you can do the double slit. So the double slit experiment was first done by Young back in a while ago. And you shine light through two slits and you see an interference pattern and you're like, oh, hey, light's a wave. That's cool. And you can do the same thing with atoms. And for example, if your atoms are all cold enough that they're in a Bose-Einstein condensate, then they'll just sort of do that on their own. But you can make atoms, the atom, if you send it through slits, you might think it's either going to go through this one or it's going to go through this one. But it doesn't. It goes through both of them because the atom is not just a particle. It's a wave function. It's delocalized throughout space, and it behaves as a wave. And the behavior of that wave, that matter wave, is determined by the Schrodinger equation, which is like the Schrodinger equation is the equivalent of force equals mass times acceleration, but for quantum mechanics.
Okay.
And it allows you to make it allows you to exactly evaluate how things like magnetic fields and things are going to affect that wave. If you have the atom and you affect it in some ways, then you can do one thing that you can do is you can split it apart into two, and then you can bring it back together, and that's basically like the double slit experiment. But if when you split them apart, you do something to this part of the atom over here, and then you bring them back together, and then you take that picture by flashing on the laser and collecting it with your camera, it's going to look different, even though you didn't like do anything. You just sort of sent this one up like a little bit higher or something. I don't know if that was helpful.
It blows my mind. I mean, I just have all of these. It's like the way that we look at things around us, we kind of, and this is maybe a stupid thing to say, but it's what I was thinking when you're saying that. We think of reality as being a certain way, but when you look at things on the atomic level and quantum measurements, it's not what you don't. Your reality is not reality anymore. It functions on a different level.
Exactly, and it just does. It just does, because it turns out that our brain did not evolve to understand intuitively the world according to quantum mechanics, because we had to, really try hard to find anything that behaved according to quantum mechanics. And quantum mechanics, the formalism of quantum mechanics is less than 100 years old. It's 99 years old, so that's actually going to change next year, because the formalism of non-relativistic quantum mechanics basically emerged in 1925. But a quantum measurement, I would say, would be a measurement where classical physics doesn't cut it anymore. You need to understand how things behave quantum mechanically.
Yeah, well, I mean, it's funny because I didn't think we were even going to get into the double slit experiment I remember that stayed with me when I was young and learning about it way
Yeah.
back, because I could not wrap my head around it. It was one thing, but it goes through two things. That's how I was trying to. You can't imagine it. You can't.
Yeah.
The way you just explained it is actually the best way I've ever heard it explained. That it's, first of all, it's a wave. A
Yeah.
wave doesn't have to be here. It can be kind of linear in a sense. So it would go through both at the same
Yep.
time. That was the best way. No one has ever, I know that sounds weird, but no one has ever explained, they've tried to, but not explained it in that way. And that made a heck of a lot more sense. I wish the teenager that first learned about it would have had someone say it in that way.
Yeah. You should take very seriously the statement that matter and particles behaves like a wave. You should also take seriously that they behave like particles. I have heard some people say it's always a wave, but if you send a this, by the way, is true for photons, which don't have mass and aren't matter technically, as well as for atoms. But if you send a single photon onto a camera, and you know that you sent exactly one photon, which you can do. There are ways that you can be very confident that there is exactly one photon that is going to hit this camera in a given time period. And if you know that, you're going to measure that photon on one pixel. You're not going to measure it spread over a few pixels.
Mm-hmm.
You're going to measure it on one pixel. And even though when it hits the camera, it's sort of spread out and delocalized, and exactly how it goes from being spread out and delocalized to producing a measurement that is consistent with it being at one location is the so-called measurement problem of quantum physics. And I'm an Everettian, so I tend to subscribe to the many worlds interpretation, where it's not actually a problem because all of the different things like are happening. But the way that it's often taught, and the way that I was taught in high school and in college even, was that according to the Copenhagen interpretation, that yeah, that the wave function just collapses.
Mm-hmm.
And you're like, how does it? Shut up! Don't ask questions. It just collapses. Shut up and
Right.
calculate.
Mm-hmm.
And there's a lot to be said for shut up and calculate, because it gets you results, but it doesn't answer the question. But because if you try and measure the position of it, you don't measure a delocalized wave with a single measurement. You measure it at a spot. So in that way, it behaves as a particle in that way. I don't think that that's a wave-like behavior. If you want to see the wave-like behavior, you got to use a lot of them and get statistics. But each individual one will behave like a particle when you measure it.
Wow, this is so awesome. All right, so I have a couple questions really quickly. This one actually came in a little bit ago. So it's from Al Trucker. Quantum computers will destroy our bank security. Why, Vandy?
Yeah, so I don't think they will. I think they'll make bank security better. So you can do things with quantum, and I think this is something that people are trying to turn it into like an actual product. You can encode. You can create codes or encryptions that are not necessarily impossible to crack, but they are impossible to crack without the two people knowing. So if you have Alice and Bob and they're trying to send a message, and then you have a bad actor, Eve, in the middle who's trying to eavesdrop on the message, then with normal encryption, if Eve is successful, you don't know. There's no way for you to know. Whereas with quantum encryption, if Eve is successful, suddenly the Bob gets a different thing, and they're all like, okay, wait, our security has been busted. And that is, and that security, the fact that you can have a system that does that, that is rigorous according to the laws of physics. Like there's not a loophole as far as we know, and if you find one, you'll get a Nobel Prize. Of course, it still depends on a machine that's doing the thing, and you can always make a machine like convince an operator that it's doing something else. But yeah, you can do things. It allows you to create things that are secure in certain ways against attack.
Okay, that's a great answer. Thank you. And our next one is from Wes again. If you change polarity in the slit experiment and get interference, is there anything that comes to mind on what it would be?
Polarity of what?
Wes, you're going to have to answer that.
Yeah.
All right, we will hold off. I'm just going to put that to the side. All right, so we've touched on a lot of different things. Oh, wait a minute, Wes he says electrons, the polarity of electrons.
Well, so you can do it with electrons. So I'm still not entirely quite sure what specifically is being asked. If you send an electron through two slits, and you do this over and over and over again, then you'll get an interference pattern. If you send it through a slit, and like if the electron is spinning in a certain way, and when it goes through slit A, it gets deflected down, whereas when it goes through slit B, it gets deflected up, then you would get a different thing. But what's actually happening there is then what you're really doing is you're doing your measurement. You're doing one measurement at the slit, because now it's not behaving the same way. But that's my best guess for.
So he did come back and say that he might be wrong. Photons is what he said right before you. So
I think you can do that with any polarization. Yeah, I think if you have a double slit and you have photons, you can have them polarized however you want.
Okay.
If you have a piece of glass or quartz in one of them that changes the polarization, then you won't. And that might be what he's getting at.
Okay.
You could have a piece of glass that changes the polarization only when it goes through one thing, and then the different parts of the wave function that have gone through, those aren't going to interfere with each other because they have orthogonal fields. So I think in that case, then that would work. I
think Wes just kind of blew our minds right there. That question. Good job, Wes. Good job. So I wanted to ask you, we have a little more than 15 minutes, and I really wanted to know about the future of your field. I'd like to know, is there anything that you're excited about in the future of your field? What's kind of on the horizon?
Oh, yeah. I mean, I'm always excited for basically technologies and stuff that will make like the sort of machines and stuff that I run small, cheap, available. So then instead of spending, years painstakingly getting all of the different lasers to work and everything and fixing the thing every time it breaks constantly, you can just buy a thing, press a button, and just create ultra cold atoms, and then start there and do that and do fun things with it. There's so many different things in physics that I think are on the horizon. a little bit further away from my particular field. I mean, we had a big kerfuffle last year about a potential room temperature superconductor.
Mm-hmm.
Eventually, we're going to get one, and it's going to be a game changer. It really will. And I would really like to have what I really want is I want a mirror that has a little photo detector on the back of the mirror. So then that then connects wirelessly to my computer. And then I can just know where the beam is on every single mirror in my experiment. And I can just align them all for my computer instead of having to go over and turn the knob and look at the thing and like not blind myself. So yeah. But as for like, is there any like big specific result that we're sort of like trying to get to? Yes, we want to measure gravitational waves with ultra cold atoms, because if we can measure gravitational waves with ultra cold atoms, we're going to be able to measure gravitational waves at frequencies that other things can't measure them at. Right now, we can only see gravitational waves when they're high frequency. And if you can see them at lower frequency, then you can watch them for a long time, pinpoint exactly where in the sky they are, do some math, figure out, okay, this little wiggle in my signal is being caused by two neutron stars orbiting like at this rate, and they're spiraling in closer to each other. And we can fit that to a model, and then we can say, okay, everybody, according to these measurements over the last 3 months, we are pretty sure that at that exact spot in the sky at 2 p.m. next Wednesday, there is going to be a neutron star collision, and everybody should point their telescopes at it so that we can watch it from start to finish. Because that's awesome. That's awesome. That's awesome.
that really is awesome. That's really cool.
Yeah.
Well, no, I'm not going to say that because you're not a black hole specialist. I love black holes. I absolutely love learning about black holes, and every time I have a show, I try to move it into black hole talk, and I'm not going to do that to you. But everything you're saying right there, I'm like, oh, maybe we can learn more about what a black hole actually is, and be able to take some measurements that we've never been able to take before. I think that would be badass.
Yeah, absolutely. Yes.
So I'll stop with that stuff because I always tend to go there. The last question I have is not even on my list, but it's something that I've been wondering about. What is the most frustrating thing as far as what lay people think about science these days and about physics these days?
I think maybe that the answer should be that answers should be both easily understandable and completely true and accurate. My PhD took me 8 years and a lot of math and a lot of careful, tweaking a little knob over here by a little bit, and then tweaking it a little bit back in order to get the system to work. And when people want it all packaged, so you give them a very straightforward yes or no answer that is always going to work all the time, that's just not how it works. It's not that simple. The answer is, it depends. The answer is, there's a subtlety there. The answer might be, you can think of it in both ways. Because sometimes you can think of it in both ways. But that also doesn't mean that one of those ways is not clearly better. Okay? You can reconstruct the entire coordinate system of the entire universe with the center of Pluto as the center of the universe, let alone the center of Earth. You could do it with anything. That doesn't mean that that's the best way of thinking about it, okay? Like, and also, yeah, basically the expectation that things should be easy, and that that you can acquire the same, you can acquire a level of understanding in 3 days using YouTube videos that is going to actually give you insight comparable to people who study these things carefully and closely and are wrong a lot. It can be frustrating. I spend a lot of time interacting, or at least observing, flat earthers, and it can be frustrating. And also, everything that I just said for like the last 2 minutes there, it also frustrates me that people think that means that I'm arrogant and that I think I'm better than them. And
Right.
I'm like, no, I'm not. I'm just saying that you're asking questions. If you had a sick universe and you had to take your universe to a universe doctor, you wouldn't take it to a guy who figured it out on YouTube. Just like if you have a sick person, hopefully, turns out people do actually go to quacks, but you're not. If my car is broken, I'm not asking Jim Bob, who thinks that engines are a conspiracy, how to fix my car. I'm going to a mechanic, and I don't need to know how it works or any, like, yeah, I'm just kind of trust them, because I ain't got time for that.
Nobody got time for that. I knew you would have a great answer to that with, your work on Bad Science Sundays. And there are so many things that frustrate me. And I'm not even a scientist by any stretch of the imagination. I'm just someone who does a YouTube channel. But it frustrates me as well that I see it all the time, every day. People say, well, I've done my own research. That's the big thing. I've done my own research. And so they are more knowledgeable than not just someone like you who has had those years of experience, but we're talking about the last 100 years of experience that's built on top of each other to get us even more knowledge. And it's like, really?
Yeah.
So, yeah, that's interesting.
Also, the idea that maybe they're right, and somehow we've all sort of convinced ourselves about this big house of cards that doesn't actually work at all. There are problems in modern physics. There is a crisis in cosmology. There's some. I mean, the Hubble tension is one of the biggest confusing problems, and it's very exciting in modern physics. And people who say that there aren't people working on every different way that you can think of making new models, they're just wrong. We don't just take Einstein as gospel and keep going. We really don't. I know that people think that, but we really don't. If you think it's all wrong, provide a model that is comparable in explanatory power.
Right. Absolutely. I think the coolest thing about science is the fundamental goal is to prove yourself wrong, in essence. And that's how you find not truth, because we never do really find the full truth, but it's at least you're learning something that does happen, and you're also eliminating the things that don't. And I just think that that's such a cool thing. So, all right, your final words for our viewers. This has been so much fun. I can't believe it's already almost up. So what are your final words for all of our viewers?
Go and subscribe to Maya Adkisson's channel. and will come and watch us on Bad Science Sunday. But also, science is awesome. Science
Yes.
is really cool. I think it's great. I think also that, it's okay to be wrong. But don't get too discouraged by all the people who are so good at being wrong, because, we're all wrong sometimes.
Yeah.
But the earth isn't flat, people. It's not flat.
No,
Okay.
it's not.
It's not.
That was great.
But kind of maybe the earth is in the center. It kind of depends on what you mean. But
Yes, absolutely. Absolutely. But I think the greatest thing is to be able to not only say that, not only acknowledge it's okay to be wrong, but to acknowledge when you're wrong, and
Yeah.
and make it okay for everybody. So I like that
Yeah.
answer from you.
Yeah, and it's people are so afraid of being wrong that they'll double down on positions that they shouldn't double down on.
Mhm.
And they won't acknowledge that they're wrong. And
Yeah.
I understand that. And scientists tend to be better than most people, in my experience, at being willing to acknowledge that they might be wrong. It's but not about things like the shape of the earth. Like, you don't understand how many things would have to be. The only way that the earth could be flat is if I am actively in a delusional state right now, and my entire perception of reality is false. Otherwise, there's just no way. There's too many things that obviously disprove it. It's like saying, yeah, but maybe the sky isn't really blue in the way that everybody understands it to be blue. Like, what does that mean? Like, yeah, maybe, but the only way that could work is if you're insane, and that's why you think the sky is blue, and then you're wrong about everything.
Yeah. I just want to say you're absolutely awesome. I have had so much fun on this show tonight, and I know that all of our viewers have too, because the live chat has been fantastic. Everyone's been having a good time. So I want to thank you. I would love to have you back on again. You're just a lot of fun. Maybe you can bring Maya with you, and we could just have a whole big fun time on the sunny spot.
Yeah.
So
I've also noticed that you've had you have a lot of physicists on this program. You know a lot of physicists.
Now I do. It's a lot of other people who bring them to us, and I really love that. And Wes is awesome with finding people. So we've been very fortunate. But if you ever want, if you want to be on a show with someone that we've had on before, let us know. We can try to hook that up. That would be kind of cool.
Yeah.
So if all of you enjoy this, and you thought that this was a great time like we thought it was, support us. And you can do that simply by subscribing, liking, hit that bell so you know when a new show has come out. If you really want to help us, we are on our way to becoming a 501c3. So our patrons are so important to us, and we want to thank you. We have Eric Ozols, Rion, Deneen Murphy, Dan D, Michael Wiseman, Kathy Cotton, Cindy Plaza, me, Aaron Coalson, Phil Calderone, Amanda McLeod, and Logan Fisher, our newest one. Thank you, Logan. So all you have to do is check us out, and every little bit helps. If you aren't able to, again, just subscribe. It's really cool. Don't forget to check out our other shows on Skeptic Haven. We have Thursdays, of course, with me, the Sunny Spot. We have Saturday with the Global Atheist, which is awesome. We go all around the world, talk to people. And we also have Women Atheist Unload, and I'll be on there this Saturday talking about abortion. So, and then we have our call-in show, Let's Talk, on Sundays. So we have something for everybody. We have the science and the geeks, and we also have the people who are just, wanting to get out there about atheism. So, it's something for everybody. So in the meantime, remember, everyone, to always think critically. Good night, everybody.
The colors in the flower evolved in order to attract insects to pollinate it is interesting. It means that insects can see the color. It adds a question. Does this aesthetic sense also exist in the lower forms? Why is it aesthetic? All kinds of interesting questions which the science knowledge only adds to the excitement, the mystery, and the awe of a flower. It only adds. I don't understand how it subtracts.
The equation E is equal mc squared